He said, I'm Jason Bonior. I'm with a signal processing engineer with RedWire Technologies. And I was hoping to give a short talk on going through and reverse engineering a wireless signal. So my goal here was to really gear something towards people who are a little bit newer to GNU radio, or at the very least new to analyzing a wireless signal that they haven't seen before. And at the end, to have a little bit there for those of us who come that they're interested in maybe doing something with the data, but aren't necessarily focused on the radio side itself. They just want to be able to get some data to perform some other sort of analysis. So when you're looking at a signal you've never seen before, or you're approaching some sort of a device, you're going to go through several steps. The best is always going to be to start with some sort of a documentation. From there, you're going to move on. If you can't find the answers you need, looking for it in the frequency, modulation, coding, and so on. When we get to the end here, I'll talk a little bit about the flow graph I have and how I went to display it, and hopefully give a live demo. But we'll see how that goes. So as I said, the first thing you're always going to want to do is look at documentation. Has somebody already done it? In a lot of cases, there's really good out-of-tree modules already out there. If you go look on Cgrand, there's tons of stuff that's already been done, and it's great to start from that and kind of move forward. Sometimes there's other libraries that exist written for other tools. You might find something, there's a project on GitHub called RTL433 that has a lot of radio applications. Sometimes, even if you're not going to be using that particular library, the source code and the comments in the community there can also be very helpful to get you started. And in some cases, you can just apply a wireless tool, like a Flipper Zero, for things like key fobs and so on. A lot of those protocols might already be programmed in. And if nothing else, it can tell you what the packet, that data is actually supposed to look like, which can kind of give you a target to work towards as you're looking at your signal. And finally, failing all that, there's always, assuming you're within, the device is made to be sold within the United States, there's the FCC ID. And if you look that up, from there, all the documentation that they have to supply is going to give you your operating frequency, a basic operational description. You have access to testing reports to show compliance for the device. And in some cases, if you're really lucky, I've seen some with schematics, bill of materials, even board pictures, block diagrams. A lot of times they will file paperwork so they don't have to share that. But every now and then you luck out and you basically have everything you need. So as I said, first step, you're going to want to find the thing in frequency. So in my case, I was playing with a little barbecue thermometer. Goal here to see if we can get the temperature values that are being transmitted over the air. In this case, it does have an FCC ID, which helped me narrow down where to look. If you don't have that, best places for things like this is you're going to start with a lot of the common bands, 433, 900 megahertz, 2.4 gigahertz, and kind of look around. If you can mess with the sensor, turn it on and off, so on, you can verify what it is. In my case, once I've managed to narrow down where it was, in the 433, next step was to go on and see if I could figure out the modulation. So you can kind of see, I should have mentioned before on the other slide, but you can see in the bottom there, it's just got one really strong peak, which usually implies some sort of ASK. And sure enough, if you take a magnitude, use a complex to magnitude block and look at it in a time domain plot, you can see that we get nice spikes going up and down. Heavily implies that it's going to be ASK again. So zoomed in a little further, and sure enough, you can see those are really nice looking on and off, really nice ones and zeros. And if you look at it, there's something else you'll notice. There's a really nice pattern to that data. There's never more than one or two ones or zeros, which would usually imply something like a Manchester encoding. So in this case, going from a 0 to a 1 is a 0, a 1 to a 0, a 1. So if we try applying that, we can then look at the bits that come out, vary the temperature by messing with the temperature probes, and then we can start looking at the packet to try and find out what's actually going on in the packet. But I ran into one little trouble here, and I don't know if you guys can notice the pattern to all that data up there. I only ended up with hex values of A6, 5, and 9, which looks a lot like Manchester still, which led me to think that maybe something was wrong with the block, went back through my block. It appears to be demodding. I went so far as to uh, print off the time domain plot you saw there and go through by hand and decode it. And sure enough, this is what you get out of it. Which left me a little confused. So decided to try just doing it again and see what comes out. Ended up with data that looks a lot more reasonable. I don't know about anybody else here. I've not encountered double Manchester or maybe some other encoding, and I just got lucky with that. But in the end, I ended up with a packet that looked much more reasonable. So, as I mentioned before, the thing to do would be to vary the, here, I'll back it up. Vary the, in this case, vary temperature, or in some ways the sensor state, so that you can see what kind of changes that produces in the packet. In my case, the numbers you can see on the left are going to be your, are the temperatures of the two things, or the two temperature probes in Fahrenheit, and then the resulting packets. Playing with that a little bit, I found that the first nibble of the packet is always going to be a 2 or a 7. A 2 under normal operation, a 7 if I push the resync button on my thermometer. The temperatures always seem to vary in those same, in the next five characters, and the last 4 appear to be the checksum. And those in particular narrow down on being the checksum, because as varying the packet values, a change of 1 bit would change those 4 nibbles quite a bit. So my first assumption would be some sort of a CRC. And I don't know if anybody's used CRC, I would say Revenge or reverse engineering. It's a nice command line tool where you can plug in multiple packets and it will calculate or basically brute force and tell you what CRC algorithms fit. So I took a few packets, plugged it in, and got nothing. So that was very frustrating. So my next assumption was, okay, it's some sort of an XOR mask, some sort of a checksum, other checksum is being applied, and I started collecting packets. When I ran into another problem, you can see I have 2 packets up there. The packet type and the temperature data are all the same, but they have different checksums. That one really confused me as to how you would possibly get it wrong. So, do I have something else going on there? But those 2 different checksums come from when you press the resync button on the thermometer. Every time you push it, you'll get that 7 I mentioned for a resync message, and that checksum will be different from that point forward, even for the same data. Now, at this point, I was getting pretty close to the conference, so I went Googling around to see if I could find, following my first point there with documentation, see if anybody else has done this. Found some other people playing, trying to different projects, playing with the same thermometer, and on the Adafruit forums, I came across a user named Nibbler who has a great post explaining how they worked out what the algorithm for this checksum is. It's actually an XOR mask that changes, it's calculated from a linear feedback shift register, and that's applied to the data, and the result will give you a session ID, which is how the thermometer syncs to its receiver. I was going to give a quick overview of how they calculated that, but there is so much there, and it's so well written that if you're interested, I would encourage you just go find it. I have the link at the bottom and at the end of the presentation. They put a ton of work into that. And anyway, as we took that, rolled it into the flow graph, and so I end up with the final flow graph. Taking the data in, taking a complex to mag, slicing the bits. In this case, I'm then the multiply by 2 and subtract 1 is to make the bits differential. That way I can feed it into a correlator and look for that preamble pattern at the beginning to line up to wherever the packets are. Once I have that, I feed it into a Manchester decoder, and that data then goes into a parser I wrote, which takes the data out, breaks the packets apart, and passes it on as a PMT to another block, which is the packet to 0MQ, which formats the data in a nice JSON format, serializes it, sends it out over 0MQ to a web server, which is then updating a web page so that we can remotely monitor what the temperature is. There's just a little quick picture of the web server running there. I'll bring up an actual demo though, as opposed to just a screenshot of it. But as I'm trying to bring up the demo, if there's any questions, the code for both of these or for everything that I did here is available at RedWire's GitHub page. The link at the bottom is the one I talked about. It really is a great article talking about how that individual reverse engineered that checksum. It's worth a look.